All right, let's jump straight into this architectural walkthrough. If you've been working with agentic systems for any length of time, you know the absolute frustration of building agents that process continuous input but completely fail to form any sort of coherent autobiographical timeline. It's a massive headache. So today, acting as your technical lead for this explainer, I'm going to walk you through the core of our Nemori 3.2 architecture. We're going to see exactly how we solved the goldfish memory problem and moved way past basic indexing into true dynamic memory evolution.
Here's the blueprint for today's explainer. We're hitting escaping goldfish memory, the watershed model, three-gate boundary detection, context and surprisal, the meme evolve bridge, and extracting the library. Let's get right into it.
Section 1. Escaping goldfish memory. First, we really need to understand the fundamental failure in standard agentic memory systems today. Think about how most agents operate right now. It's basically the cognitive profile of a goldfish with a search engine. They have incredibly fast lookup, sure, but absolutely no autobiography. They either read floods of tokens and immediately forget them, or they rely on some bolted-on vector database. But here's the thing. Streams produce events, and events are not memory. If an agent just indexes facts without the temporal arc that actually gave those facts meaning in the first place, well, it has no real autobiography. It's just doing fast lookups on isolated chunks of text. So we had to build a system that avoids two major extremes. On one hand, you have continuous stream ingestion, which just floods the system and forgets everything. On the other hand, you have standard vector stores, and honestly, those just leave a contextless siltbed of facts. Imagine a user mentions a vital clue at minute 4 of a conversation, and it suddenly becomes relevant again at minute 47. A standard system, stripped of any temporal arc, is just going to return 5 disconnected paragraphs that happen to contain matching keywords via cosine distance. That is not episodic memory. Section 2. The Nemori watershed pipeline. To fix this, we had to completely rethink our macro architecture. Enter the watershed model. Instead of discrete static calls, the Nemori river flow actually moves data through a 4-stage enumeration. Think of it literally like a watershed. Source events merge into tributary episodes. Then, those are promoted into main river journeys. Finally, the river slows down at its mouth and deposits facts as a semantic delta. To actually make this work with continuous streams, we built this axon-like discretizer. It chunks the stream into 50-token neuronal packets that carry dynamic data like spike density. This is a game changer because it allows us to route them efficiently through hop-field attractor basins without constantly having to reevaluate the entire stream. Section 3. Three-gate boundary detection. Now, how do we actually pull this off in practice? The crucial point here is segmenting this continuous stream into episodes without burning through a mountain of tokens. The original Nemori paper assumed episodes were already perfectly segmented for us, but in the real world, yeah, they aren't. So our extension layers 3 independent gates. First, an SEM boundary probability exceeding 0.5. Second, an active inference surprisal spike above 0.8. And third, a resonance check returning dissonant or turbulent paired with a surprisal over 0.6. If literally any of these 3 signals trips, the system deterministically forces a boundary cut. And here is why that matters mathematically. By deterministically cutting boundaries with this 3-gate detection, we save roughly 600 tokens per evaluation pass. 600! We make the segmentation decision before a single LLM call is even made to construct the episode. In high-throughput agent environments, that token saving is absolutely massive.
Moving on to Section 4, Context and Surprisal Signals. Let's look at the kernel.
Once we have an episode, the kernel predicts what should be confirmed by the experience, calibrates it against the actual log, and emits 3 things: new facts, surprisal, and something we call symbolic residue. Symbolic residue is completely crucial. It's a dictionary of active goals, active entities, and stable context. It's what maintains the situational context across consecutive episodes. Without it, the agent would feel like it's waking up from amnesia or reading 2 strangers' diaries. See, when you distill an episode into facts, you naturally strip away situational context. But this residue is explicitly carried over. In our token budget manager, this active residue actually outranks passive facts, making sure the agent keeps its immediate situational awareness even as the older facts start to decay.
And surprisal, it isn't just some passive score sitting in the kernel. In our system, a surprisal signal over 0.6 literally propagates as a currency that manages arousal and dissonance system-wide. When the calibration step detects that something was unexpected, it doesn't just quietly log it. It actively updates the arousal-surprisal cache to increase biological agency on the next cycle, fires the hexus dissonance signal to tell the global coherence engine that the system is uncertain, and triggers a meta-evolution cycle.
Section 5. The Mem-Evolve Bridge. This is where memory stops being static and actually starts adapting.
We need to look at how Nemori talks to the rest of the substrate through the Mem-Evolve engine. The really interesting thing here is that these two are entirely decoupled. Nemori is the ingestion side pulse. It takes in the world and writes the experience. Mem-Evolve, on the other hand, is the substrate evolution heartbeat. It looks at where the agent failed to predict an outcome and actively handles the closed loop of diagnosing and redesigning the memory schemas so it doesn't happen again.
So how do they connect? They couple exclusively through a trajectory protocol. Whenever an episode finishes successfully, or when we get that high surprisal event over point 6, Nemori packages the data into trajectory data objects and hands them off via the Mem-Evolve adapter. But because they're totally decoupled, we have to be incredibly careful about feedback loops. Actually, we use a mechanism called cascade guard at both ends. It's a content hash deduplication setup that ensures Nemori distilled facts aren't accidentally re-ingested by the system in this infinite continuous loop.
Which brings us to our final section, extracting the Nemori library. Because of that incredibly clean decoupling we just talked about, we were able to review the recent audit and commit 1D3D16E8. We realized the Nemori River algorithm was robust enough to be its own independent entity. So, we've defined 3 strict protocol seams that form the boundary for extracting this into a standalone library, while Myonisys implements the protocols. The library defines the signatures. Base and backend handles the routing, memory store persists the episodes via graffiti, and Event Bus manages the narrative subscriptions. The ultimate extraction goal here validates that our algorithm is an original implementation capable of serving as a strictly version-pinned dependency. By extracting this into a standalone, Apache 2.0 licensed Python library, we enforce a strict architectural boundary. The river never needs to know what Mem-Evolve does internally. It only knows that it accepts standardized trajectories. Honestly, it's a massive leap forward for modular, autobiographical agent architecture.
I want to leave you with this provocative thought to consider. If a single model call can synthesize both fact and surprisal, what happens when the agent's memory substrate starts evolving faster than the stream itself? As our Mem-Evolve loop accelerates, how will a fully dynamic memory substrate redefine what it means for an agent to have an autobiography? Because when the system is actively redesigning its own methods of retention based on those surprisal signals, memory isn't just a record of the past anymore, it becomes an active prediction engine shaping the future. Think about that as you implement these patterns in your own architectures.